Today we're going to review the theory of operation for the spectrum analyzer. Alright, so on this slide what we have here is a representation of what you would see on an oscilloscope if you fed an audio signal into it. Unfortunately, this waveform doesn't really show you everything that's happening inside this waveform. There's a lot of hidden information that you can't see. What does it show us? It shows us amplitude in this axis, or loudness, and it shows us what happens over time on this axis, because this signal is constantly moving this way. If there was a way that we could peer into the oscilloscope this way and dissect the waveform, what we would see is thousands or hundreds of thousands of waveforms that coexist with each other. This low frequency waveform, this could be somebody pressing a low bass note on a synthesizer. Its neighboring frequency, this could be like a hand clap or a tambourine, and this higher frequency, this could be somebody striking a snare drum. But if you looked at the sum of all of these waveforms, what you'd end up with is this flat two-dimensional waveform that you see on a typical oscilloscope. But what if there was a way to look into the oscilloscope from this side? If we had a magic window into the oscilloscope, if we were able to look at the face of each one of these waveforms and kind of follow the height of the waveform, it could be represented by this little peak here. Same thing with the next frequency. If we looked at it from this direction, looking in, based on the amplitude of this waveform, we could get this peak here. And same thing with the third frequency. Notice how we're being kind of selective here with the frequencies that we're choosing to look at. The same thing happens in a spectrum analyzer. In fact, the spectrum analyzer is exactly this, except it might be focused on more bands than just these three. So now let's look at what's happening inside the spectrum analyzer. Now, there's more than one way to do spectrum analysis. We're just going to review the method that we're using in this project. Okay, we got some key players here, some dedicated specialized hardware. There's a integrated circuit here that I like to call the slicer. This is a highly specialized piece of kit here, and it focuses on one task. And its task is to take an analog input that it's feeding in and slice that analog input into 7 distinct bands. It'll analyze those 7 bands, and then based on the amplitude or loudness that it finds within each one of those bands, it will give us some feedback on this output line. This output line is feeding an Arduino. Arduino is like a super cheap, super inexpensive PC running at 16 megahertz. Arduino, and with respect to this project, is kind of like a timekeeper or a traffic cop. He sets the pace at which the slicer IC works. So he's receiving information from the slicer, but he's also commanding the slicer to do things at certain intervals. You notice there's 2 lines coming out of the Arduino going to the slicer IC. And when this project is first powered up, the Arduino does a little bit of housekeeping, and then right afterwards it goes in a continuous loop. And the first thing it does in that loop is it sends a signal to the slicer IC via this reset line. It'll pulse this reset line, and the slicer IC will recognize it as a command to say, hey, let's start from scratch. All right? And on this other line, the next line, I like to call it the next line, but it's actually a strobe line. when this line is pulsed, the slicer IC will say, okay, Arduino, I recognize that you want me to examine the next band. Okay, so slicer IC can analyze 7 bands. So we can call them band 0, band 1, band 2, band 3, all the way up to band 6. Remember, 0 through 6 is 7 positions. You count the 0 as a spot. Or we could call them slots. In a typical configuration of this chip, the slots would look something like this. Slot 0 would focus on frequencies that surround 63 Hertz. So it's not only looking at 63 Hertz, but it's looking at its surrounding frequencies. You know, let's say, for example, 30 Hertz to 90 Hertz. Slot 1 is its own little bucket of frequencies. It's focused on frequencies that neighbor 160 Hertz. Slot 2 focuses on frequencies that are in the neighborhood of 400 Hertz. Slot 3 is 1 kilohertz, and so on and so on. Right, so if we can imagine that there are 7 slots inside this chip, the Arduino can tell the slicer IC to reset and start at slot 0, or it can tell it go next and go from slot 0 to the next slot, or the next frequencies. And the Arduino is cognizant or aware of how many slots the slicer IC has. So every time Arduino sends a next pulse to the slicer IC, it increments a counter and it keeps count. So it starts at 0, receives some information from the slicer IC, then says, okay, I'm ready for the next one, gives a next pulse, slicer IC goes to the next slot, feeds that information out to the Arduino, and the Arduino says, okay, I'm going to store that information, let's move on to the next one, gives a pulse on the next strobe, and it'll do that over and over until it gets up to the last slot. And it recognizes it and it says, oh, slicer IC is at slot 6. That's its last possible slot. Let me send a reset pulse. And it'll send out a reset pulse to the slicer IC. Slicer IC will then return back to slot 0 and perform the whole thing over and over again. This loop of starting at slot 0 and going to slot 6 happens hundreds of thousands of times a second. I mean, it's lightning fast. So every time the slicer IC sends some information to the Arduino will take that information and store it in a table. Okay. Let's look at how the slicer IC works in a little bit more detail, and we'll come back to the slide. All right. So slicer IC, we know, has 7 slots, or 7 frequency bands, or whatever you want to call it. Okay, and the first thing Arduino does after it's powered up is it comes and sends a pulse to the reset line. Reset line will basically kill all these filters except for this filter here. These are 7 filters. Each one of these filters is basically filtering out a specific range of frequencies. They're tuned filters. So this filter here will, in a typical configuration, be focused on the 63 Hertz range. And this filter here will be focused on the 160 Hertz range, and so on, until we get to the last filter, which is kind of focused up on the 16 kilohertz range. Okay, so after the reset signal is set, all of these filters are turned off except for Q0. Now Q0 is receiving audio in real time, and it's sending the audio through some circuitry for analysis. This circuitry is going to measure the amplitude or loudness of just the frequencies that are coming out of this filter. And it's going to convert that amplitude or loudness into a voltage. Now that voltage can be from 0 to 5 volts. 0 being an amplitude of nothing or silence, and 5 volts being a very loud signal for this particular frequency band. Okay, so after reset is hit, this is the only filter that's on. Well, next thing the Arduino does after it's received this voltage is it sends a pulse to the next line, or the strobe line. And all of these filters are turned off except for filter 1. Filter 1 is focused on a completely different set of frequencies, and it's filtering out everything else outside of those frequencies. Again, it sends those frequencies through some circuitry that analyze and measure the loudness or amplitude of just these frequencies and converts it to a voltage from 0 to 5 volts. And then that voltage comes out and gets sent to the Arduino. And it does this again and again and again and again. So after this thing has cycled through this one time, you might end up with an output that looks something like this, depending on what the amplitude of this the input waveform was. And if you take a close look at this kind of looks like columns in a spectrum analyzer, and that's exactly what you're seeing. If you can wrap your head around what's happening here, the rest is cake. This chip, the slicer chip, is kind of a buffer too, because if you look at the voltages that you would see like at a line level output from, say, a receiver or something like that you're feeding into this chip, it is crossing from 3 volts past 0 down to possibly negative 3 volts, and it back up over past 0 to positive 3 volts. And it's, audio is like that. It passes from 0, goes up, comes back down, past 0. So it goes into a positive voltage range and a negative voltage range. Well, Arduino doesn't talk in negative voltages. Arduino only knows 0 volts as off and 5 volts as extremely loud. In fact, Arduino really only understands ones and zeros, but Arduino has something in his arsenal called an A to D converter, which is a little piece of circuitry in there that will convert the voltage of 0 to 5 volts to a binary number of 0 to 255. It'll map 0 volts to binary 0, and it'll map the maximum voltage here to binary 255. So Arduino has some tools in his arsenal to work with ones and zeros, because that's what Arduino likes to work with, ones and zeros. Arduino definitely doesn't want to deal with negative voltages. In fact, if you feed negative voltages to some of the pins on Arduino, you're pretty certain to hurt the Arduino. But Arduino is pretty happy with voltages from 0 to 5 volts. And if you're sending voltages like this from 0 to 5 volts to one of its analog pins, which has an A to D converter, then you can actually convert these voltages in here to a span of numbers between 0 and 255. Okay. Another thing to keep in mind is that these filters are all being driven by a master clock. This is not audio. All this is a very steady pulse train. And these filters are using that as a reference signal. And I just want you to imagine that if I were to take this pulse train, let's say this was pulsing 1 time a second. If I made that pulse train go 2 times a second, all these filters would shift in frequency this way. Now, if I made each one of these pulses half the speed of what this is here now, the frequencies would shift this way. And this is how we can have an analyzer that has more than 7 bands. What we'll do is pair up 2 of these slicer chips. One slicer chip will get frequency X, and another chip will get another frequency that has been skewed. And then what happens is you end up with 7 frequencies here and 7 frequencies here, and we kind of lay them in on top of each other just like that, and we interleave them. And we take the output of each one of those chips, and we just let the Arduino know which one is for which band, and the Arduino will handle the rest. So this is probably, like I said before, if you can get your head wrapped around this part right here, then this project is going to be simple for you to understand. Here is what this image kind of looks like. My oscilloscope is giving me the middle finger, but here is what this image here looks like on an oscilloscope. And you know, this is just by chance. I probably caught it just as, you know, maybe a snare drum was getting hit or something like that. But here's 7 bands: 1, 2, 3, 4, 5, 6, 7. These are voltages from, here's the 0 line, and this up here is 5. Well, it's probably a little bit less than 5 because it wasn't at maximum loudness, but the 5-volt line might be up here somewhere. Each one of these little squares should represent a volt. So this is like 1, 2, 3, 4. It's a little bit less than 5 volts here. So this very tall column represents, let's see, that would have been on 1, this would have been on 0, 1, 2, 3, 4. So that means that in this filter here, Q4 focuses on, say, 2.5 kilohertz. Whatever was inside this analog signal had some pretty loud content in this frequency range. And this little circuitry picked that up and converted it into probably somewhere around 4, maybe 4.5 volts. The Arduino took that 4.5 volts and converted it into a number from 0 to 255. And I would imagine that for this column here, this was probably in the high 200s, you know, maybe 230, 240. Don't know the exact number, but you get the idea. And let's talk about the master clock, right? So the master clock, you know, in a typical configuration, these are the frequency bands that a slicer IC would be looking at. These are the center points of each frequency band, and notice how the frequencies taper off to the left and the right. So this is with a known master clock of X. If we had a second chip, we would send a different clock rate to the second chip, and then we would shift all these frequencies left. And you know, the first frequency might be 30 hertz, and the second one might be 100. Okay. So let's go back to this page. So now, this slicer IC is sending output to the Arduino, and Arduino is setting the pace for the slicer IC. the output of the slicer IC is going into an ADC, an analog to digital converter. This chip is converting that 0 to 5 volts into a binary number, which will be binary 0 up to binary 255. And it stores, for each iteration, each time it goes through that loop of slot 0 to slot 6, it will take those binary numbers and store them in a table. All right? Right after it finishes with its iteration, it will take those numbers and it will again map them to a column on the spectrum analyzer. All right? But here's the thing. Inside the software that was written for the Arduino, we define how many LEDs are in each column. You can have columns that are 5 LEDs high. You can have a column that's 25 LEDs high. You're only limited by the amount of RAM that the Arduino has. So once the Arduino knows that it's working with a certain number of LEDs in terms of height for each column, it will map this binary number to an equivalent height on each column. Now, luckily, most of the stuff that's happening with these binary numbers and stuff like that, you never have to worry about, because all of those functions are being handled by libraries. They're open source, but there are some amazing libraries from some very ingenious programmers. And those programmers have made those libraries available to the public, and the reality is it saves tinkerers like myself a lot of time, because I can just send simple instructions to the library and let the library worry about mapping all this stuff out. Also, the Arduino has some pretty nifty built-in functions, like converting these analog voltages that come out to binary. It has built-in functions with that, and you can convert a voltage to a binary number with a simple command like a read command, and it'll read this pin on the ADC and give you back a binary number. So now this is all of this stuff that's happening down here should not intimidate anybody, because they're all happening with functions that are kind of already set up, and you don't have to worry about getting into very intense programming. So once these numbers down here for column height have been calculated, we'll push these values out of the Arduino to an array of smart LEDs. So in this example, we had a binary 215 for column 0. It converted it into a height of 18 LEDs out of a total of 21. And so inside this serial data that we're sending out to the smart LEDs, we will light up 18 LEDs on the first column. Same thing with slot 0 or band 0. We had 151 here for binary. We're going to convert that into a height of 11 LEDs. And you really don't have to worry about all this stuff. The only thing you have to worry about is setting up these LEDs in the correct orientation so that the proper LED is being lit up when the serial data is coming out of the Arduino. All right, let's talk about the Arduino. Most people have seen this form of Arduino. This is a Arduino Uno. I believe this is a knockoff one. It's fairly inexpensive, and you could do some spectrum analysis with this. The only thing is that this particular Arduino doesn't have a lot of memory, and because each smart LED has to have a memory location to store certain information about color and brightness and its position, you run out of memory on this thing really quick. Don't forget, we have to load some pretty intense libraries in there, and plus some surrounding code, for the rest of the program. So when everything's said and done, you're not really going to get you might be able to get 70 LEDs out of something like this. So this is probably best for a 7-band graphic spectrum analyzer. Me, I want to go bigger, right? Need more LEDs. I almost have 300 LEDs in the 14-channel spectrum analyzer. And why did I settle on 300 LEDs? Well, because LED rolls come in counts of 300, so 300 just seems like a good number. If you have if you have 14 columns of 21 LEDs, you end up with like 296 or something like that. Forgive me, I'm not good with math off the top of my head. This here is a Arduino 2560. You're saying, what? That's not an Arduino 2560. Yeah, it is. This is a custom built one. So a regular Arduino 2560 is probably about this long, and maybe a little wider than this. But the regular Arduino Mega 2560 has other supporting circuitry on it. This thing has been stripped down to be kind of minimalistic. It doesn't have a voltage regulator on it, and for some, it's assuming that you are providing clean regulated power externally. And there's some other small items that are missing, some pull-up resistors and things like that. But in this application, I am putting together a board that is the exact same size as this board that will mate with it on top, kind of like they call it like a hat, a development hat. And so this board will, that's blown up, but it will be this size and will sit right on top of here. And it will have on it voltage regulation for 5 volts and 3.3 volts. It'll have some safety features. It'll have a master clock, actually more than one master clock, and it's going to have dual slicer ICs, and everything is going to be surface mounted. And that leads me to my next point about surface mounted components. Now, this master clock is being fed to the slicer IC, and it has to be a steady train of pulses. The better this pulse train is, the more reliable the output you're going to get out of this slicer IC. Now, there are folks that develop projects around the slicer IC, and for a clock train they will use a resistor capacitor network that kind of forms like a charge pump and makes a rather ugly pulse train, but it does make a pulse train. The only thing about those pulse trains is that we're dealing with very low capacitance on that circuit. So there's a tendency for that clock to want to stray. So if you're doing this on perf board or on just one of those push-in kind of breadboards, capacitor resistive network for a clock is probably not going to be reliable. Did I get it to work? Yes. Was it reliable? Yeah. I wasn't convinced it was going to remain reliable. Sometimes it wouldn't even start. It wouldn't even resonate, and it would drift. It could drift by just, you know, wherever you placed it. If it was sitting next to a piece of copper, the clock would drift. So for experimental purposes, yeah, RC clock may be good. But if you looked at my first video, you should have observed that I was using a reliable clock source in that video. I was using a function generator, something like this. Now, of course, we don't want the expense of a full function generator for something as simple as this. So on my board that I'm developing, I'm putting in a IC that is programmable, and I can generate very steady and robust clock signals. So you know, there's going to be more reliability if you go this route. Now, I'm going to provide the schematics for this at some point after I've tested everything, and I make sure, and I'm very certain that it works. I don't think I'm going to have any issues. You know, the version I made on the proto board worked well. I mean, you see it in the videos, but it's going to take me like another 2 weeks to get these things back from a board house in China, and when I get them back, I will populate the board and test it, and I'll test it non-stop just to make sure that it's going to be reliable. And once I'm sure that this is reliable, I will publish the schematics for this. I'm not going to publish the actual board file. You know, I spent a lot of hours putting this thing together. It's a multi-layer board. You know, if you want one of these boards, all you have to do is get with me, and I'll sell you a board pre-populated. I'm thinking of putting together entire kits with the LEDs, LED strips, and power supply, and everything you need, just to make it real easy, one-stop shop. But even without this board, with the schematics, you could venture off and put together your own. I mean, I'm not limiting anybody. I'm going to provide the code, the sketches that get loaded into Arduino, and you can modify them. You can do whatever you want with them. But I do have a certain vision that I would like to see. I've left some additional input pins over here. So I left those there for folks that want to get creative and add buttons or potentiometers to the project, because I'm pretty sure somebody's going to come up with a really neat variation on lighting or something like that, and I would love to have that person's work posted on a website I put together. You know, kind of like a top 10. Who has the best top 10 you know, lighting effects or something like that. I think that would be real neat to see. The other thing is, I'm going to put up my vision of what I wanted the finished product to look like. But I'm also inviting others to put their spin on it, because there's 1,000 ways you can do this, and you know, I really want to see, you know, like a community effort. You know, somebody may come up with a real inexpensive way to come up with a package to put this in, or a real cool looking thing. I hope you enjoy the one I put together. It took a lot of work, a lot of CNC work, and I'm looking forward to some feedback on it. So all I ask is that you guys remain patient. I am working on getting everything put together so that at some point we can release the sketches and the schematic, and you guys can just go crazy and start building bigger, larger spectrum analyzers. There really is there is no limit besides the amount of memory that this Arduino has. there's no limit to how many LEDs you can have in each column of the analyzer. You know, on mine I have 21, but you can go, you know, put 30, put 40. And as long as you have a power supply that can deliver enough current to keep all the LEDs happy, it's possible. The only limiting factor would be RAM in the Arduino. That's pretty easy to figure out how much RAM you have left over once you've defined how many LEDs you have in your column. You know, I think with 21 LEDs per column, I think I only utilized maybe 30 or 40% of the RAM that was available for me to use. Anyway, and I'm sure that there are some folks out there that could take that code and probably make it a little bit more efficient. I wouldn't venture off and start modifying libraries and stuff like that, but who knows. So I'm going to put some video and pictures of the current state of my analyzer, and I invite you guys to post feedback, and I will post another video soon. Thanks for watching.
Don't stop.